Hello, everyone. This is our live session for Monday, March 21st. My name is Matthew, one of the course staff for our online classes. For those of you who are here from our class, our astronomy classes, we're happy to have you. If you found us from somewhere else, we're excited that you are here with us. I posted some sort of instructions in the chat, so make sure you read that. If you have questions, post them in the chat. We'll grab them from there, and ask your questions only once. Don't worry, I'm seeing them all. I'm just curating them to make sure we get a good variety of questions and that we don't have too many that we've had before. Chris, I will let you say hello and welcome to everyone, and then we'll get started with questions.
Okay, welcome everyone to live session for the online courses, or anyone else who has found your way here. Happy equinox everybody. That's Latin for equal night. The day and night are equal on this day, and it's September 21st. So the floor is open for your questions.
All right, the very first question is from one of our live participants. Kendra Smith has some questions about gravity. Hi, Professor Impey. Can you explain how we know the effects of gravity are infinite? Shouldn't we experience the effects of every object in the universe then?
Yes, that's an interesting question. So gravity is a long-range force. It diminishes as the square of the distance from the gravitating object. That's Newton's laws of gravity, which is modified by general relativity, but that force law is not changed. And so yes, it has essentially, in principle, infinite reach. The fact that you may be subject to the combined gravitational effect of an infinite number of objects in the universe was first noted and interest by Ernst Mach, who is an important physicist and philosopher of physics in the early 20th century in Germany, a colleague of Einstein. And so this became Mach's principle. The question you've asked has been elevated to Mach's principle, the idea that we are subject, or any object is subject to the combined gravitational force of everything in the universe, since in principle out to an infinite distance the gravity is felt. In practice, however, the universe has a horizon, has a boundary of time in the Big Bang going back, and it also has a boundary of distance in the sense that objects beyond a certain distance from us are moving away faster than the speed of light. Since in the standard theory of gravity, gravity propagates at the speed of light, not instantaneously, that means that you don't have an infinite gravitational force. So it's really the nature of the universal expansion that gets around this issue of infinite summed gravity that Mach pointed to early in the 20th century.
Excellent, thank you very much. I'm sorry. The next question is from Wendy, who sent an email asking, do the orbits of long period comets go beyond the go beyond the Oort cloud, and is it thought the Oort cloud is unique to our solar system?
Both good questions. The long period comets essentially are the Oort cloud. So the Oort cloud is a largely hypothetical but indirectly confirmed quasi-spherical cloud of comets. It's the reservoir of comets because they spend most of their time out there due to Kepler's law of motion, and a very small amount if they come to the inner part of the solar system in those closer distances. And of course it's frigid. It's the zone that is hundreds of astronomical units, actually thousands of astronomical units from the sun. It's hypothetical since there's estimated to be about 1 trillion comets in the Oort cloud, and they are mostly at such large distances and they're such cold, small rocks that they're impossible to observe with a telescope. So all we can do is use the orbits of comets that are long period that come into the inner solar system to infer the population of the parent group, the Oort cloud itself. And yes, the formation process that led to the solar system, which was the collapse of a large gas cloud of order size, the Oort cloud. The Oort cloud is essentially telling us the size of the cloud of gas and dust that form the solar system. And that's presumed to be a general process, so we do anticipate that other solar systems will have their own comet clouds. They may differ in size and number to our Oort cloud, but they all should have them.
All right, the next question is from George Papadopoulos, who asks, would we know if one of the smaller planets was somehow removed from our solar system?
An interesting question, the hypothetical of how the orbits in the solar system would change if something was removed, or you could even say added. And the answer is we would know, but not immediately. If, for example, Mercury was just suddenly removed, we don't know how that might happen, and Mercury is unlikely to have a situation where it would be removed. For example, it's possible that an incoming impact from a large interplanetary body could knock Mercury out of its orbit. So there's a hypothetical mechanism, and the impactor could also go out of the solar system, and then Mercury would be gone. The simulations have shown us that if any of the planets were removed, even the smaller ones like Mercury and Mars, the orbits of the others are perturbed and become unstable actually in the long term, where long term means tens or hundreds of millions of years. So if Mercury were removed, or any of the small planets, inner planets, the orbits of the others would be affected, and they possibly would become unstable, which means they might migrate and move towards the sun, possibly into the sun, or they might move further out. The instability could go in either direction. So yes, there would be a definite effect if any planet were removed from the solar system, but it would play out over millions or tens of millions of years.
Excellent. Thank you very much. The next question is from one of our live viewers. Korat Yug would like to know if you can talk generally about some of the most exciting, groundbreaking discoveries in astronomy. And I'm assuming they mean recent groundbreaking, so perhaps in the last 6 months or year, that you find the most exciting or interesting.
Yeah, astronomy is a very active subject, of course. I think continuing to be exciting are gravitational waves detected by the LIGO project, and now there's a set of other gravitational observatories around the world. There's one in Europe, there's one in Japan, there's one in India, and there's a couple more coming online. So gravitational waves have gone from a curiosity and the excitement of the first few discoveries to almost routine occurrence. But we're learning a lot more about black hole mergers, about black hole neutron star mergers, and neutron star mergers. So that continues to be an exciting area of astronomy. I'd say what the rover on Mars is doing is exciting in several ways. First of all, it's finally, after some initial failures, it's finally succeeding in getting core samples and putting them in sealed tubes, and then for eventual deposit to be picked up by a return mission of the future. So we're staging or setting the ground for Mars sample return right now, this year and last year, and into the next year. And along the way, the rover in the Gale crater, which is a sedimentary formation where there could possibly have been life 3 billion years ago, is continuing to find strong evidence that Mars was wetter and warmer in the past, and that the place that it's landed and is exploring is indeed an alluvial formation where there was moisture, where there was deposition of sediments, and where, if it had the right instruments, which it doesn't, you could possibly detect previous traces of life. So those are two very exciting things. And of course, the biggest thing in astronomy, I suppose, in the last few months is the successful launch and deployment of the James Webb Space Telescope. Just last week, it sent back its first image from a fully focused telescope with 18 mirrors. That alignment and focusing process was not trivial, and so that was a spectacular image that it took with its infrared camera just last week.
The next question is from Jan Campos, who sent an email. If the stars in globular clusters around the halo are as old as the Milky Way itself, do we believe they formed within or independently of the galaxy? And will Webb be able to give us more information about globular clusters?
So globular clusters are important stellar populations. They are considered to be generally old populations, primordial even, dating back to the beginning of the galaxy, although there are intermediate age and even a few young globular clusters, which is to say intermediate age would be 5 to 8 billion years and young would be a couple of billion years. But we think most of the globular clusters in the galaxy, and we know this from spectroscopy of the stars, are primordial, which is to say 11 to 13 billion years old, because that's when we think the galaxy formed. And they did date from the initial formation. They form a nearly spherical distribution, and that's because the Milky Way formed from a nearly spherical distribution of gas and dust that had some small amount of rotation. So these were the first objects to condense, if you like, out of the gas and dust, the slowly rotating gas and dust, and essentially their orbits delineate the original shape of that gas cloud. So the globular clusters are in this spherical distribution that extends out to a few 100,000 light years in all directions. Now within that gas distribution, some of the gas collapsed, and with conservation of angular momentum, it formed a small disk within this larger halo. So the globular clusters trace the halo of the galaxy, which is primarily dark matter, and then the gas that collapsed and spun up to form a disk is the young population of stars that the sun is a part of.
The next question is from Jake Johnson. So their 11th grade science teacher says that we all are solar systems because we use the energy of the sun. But what is the astronomical definition of a solar system?
So solar system, when it's capitalized, refers to our solar system, the sun and its orbiting planets, and the other objects within it, such as asteroids, comets, meteors, and so on. People now use solar system in a more general term, which would not be capitalized, and that refers to the fact that we know many solar systems. We have almost 5,000 exoplanets cataloged, confirmed, and each of those is a solar system. We detect the planets, but they are orbiting stars like the sun or not like the sun, and they very often have more than one planet. Hundreds of multiple planet systems are known. So solar systems is now used in a quite general way to describe these exoplanet systems that we're finding in very large numbers.
The next question is from Mark Essex, who is on with us live. If constellations are based on mythology, why do we continue using them to describe groups of stars?
I think astronomers are traditionalists. They kind of appreciate and respect and like the history of the subject, which goes back thousands of years. So they don't have to have a direct practical purpose, although astronomers, like anyone else, if you want to navigate your way around the night sky, it's useful to use the constellations as your guide. And it's very evocative to try and imagine, as the ancient people did, that these objects, like a little set of 3 stars, one above and one below, is Orion, that's a fearsome hunter, and the 3 stars are the belt, and one is the shoulder, and one is the hilt, where he has his sword, and the star off to the side is his bow and arrow that he has raised. So you got to use your imagination. So astronomers like that history too, and the mythology, the sky stories just help bring to life, what would just be a pattern of stars. But yes, the star patterns have no completely modern functional purpose, because we know that the stars in a constellation are all at very different distances. They're not close to each other in space, because in the 3rd dimension, distance from the sun, they're at very different distances in all constellations. So it's not a physical grouping of objects. And the constellations have not changed. The modern constellations were codified by the International Astronomical Union, the governing body of astronomy worldwide, I think about 100 years ago, and there are 88 of those constellations.
Excellent. The next question is from Amanpreet Gala, who asks, how does an organism become, the question is, how does an organism become habitable on any planet? So I think it's more how does a planet, develop organisms on it? How do organisms come to live on a planet? If evolution takes a long time, does it mean that at one point we will witness at home organisms on other planets as well?
So this is a mystery. We simply don't know. We're not even completely clear of all the steps that led to life on Earth. So this is the planet we live on that we can study up close. So clearly we're not in a position to answer questions about how life might evolve on another planet, apart from the fact that we haven't detected life on another planet. So there's a lot of speculation here. We do think, however, we know many of the steps that were involved in the development of the first life forms on Earth, which happened about 4 billion years ago, maybe a little less. So there's been life on the planet for a very long time. The historical record almost doesn't exist that far back, because it's a volcanic planet with a lot of erosion and a thick atmosphere. So it's extremely hard to find intact rocks especially rocks that have not had a violent volcanic history that are that old. And that's really why we can't tell the story of how life on Earth formed. We can just make a series of plausibility arguments. And we think those plausibility arguments will hold on a habitable exoplanet, so a planet around another star that has all the same chemical ingredients as the Earth, that has liquid water as the Earth does and did, and that is in the habitable zone of its star. But that's just a projection. That's an extrapolation, if you like, from a situation on Earth that we even still don't fully understand.
All right, we have several questions about dark matter, and we often get these. So I think what I'm going to do is combine them all sort of into one section so we can cover that kind of all at the same time. And so we've got a question from Lamont Lathan and David Wells, who would like to know what are the most current theories of dark matter, and what do you think of the possibilities of those?
So dark matter continues to be a major issue for modern astronomy and astrophysics. We know dark matter exists, or something that exerts gravity but doesn't exert interactions with photons, so it doesn't have an electromagnetic interaction. We know that exists, and we know that it dominates normal matter. And we know pretty much how it's distributed on large scales in the universe. But by elimination, all we know is that it's very likely to be a new type of fundamental particle. The currently best two candidates for dark matter fundamental particles are what's called a neutralino, which is a particle that arises from an extension to the standard model of particle physics when you unify 3 out of the 4 forces of nature, all those forces except gravity. That's the lowest mass stable particle out of that unification, and it has about the right properties to be dark matter. And another candidate that's received actually increasing attention in the last year or so, as we fail to nail down what it is called the axion. That's another extension of the standard model of particle physics that was initially invoked to explain the anomalous magnetic moment of the neutron. That's a pretty esoteric piece of particle physics. But it's also a particle that has the right properties. It has the mass, it has the weakness of interaction by any other means than gravity, and it has an abundance which you need for dark matter. It has to have a similar abundance to normal particles like protons and neutrons. These are the two best candidates for probably a dozen experiments on each, trying to detect them, maybe fewer on axions than neutralinos. And at the moment, we haven't had success. We haven't detected these particles yet.
Ramani Ranganathan asks, is the distribution of dark matter random, or are there any patterns that have been observed?
There are definitely patterns in the distribution of dark matter. Dark matter exerts gravity, so it clusters, it clumps the way normal matter does. And so we expect and see that dark matter is not uniformly distributed. It's distributed on a very large scale, so we see dark matter in the space between galaxies and as extended halos of galaxies. So it's less centrally concentrated than the galaxy, the visible parts of which collapsed to the center of dark matter halos. But we do see uneven distribution of dark matter, and we can measure it directly through gravitational lensing and statistical lensing, so very subtle distortions due to gravity. And this is consistent with the fact that it's abundant matter, more abundant than normal matter, and exerts gravity, and has gone from an initially smooth distribution early in the universe to a clumped distribution, but not as highly clumped or clustered as normal matter.
Excellent. The next question is from Teflon Buddha. It's related to one of the earlier questions that we had about how gravity kind of interacts, or how it can additively combine. Can the supermassive black holes in the center of our galaxy have anything to do with the gravity that our solar system feels or undergoes, together with all the other systems in our galaxy?
No, actually the supermassive black hole in the center of our galaxy has negligible impact on the solar system. And that's because that black hole is only about 4 million times the mass of the sun. Remember, the galaxy as a whole, including the dark matter, is close to 1 trillion times the mass of the sun. And even in the central region of the galaxy around the black hole, there's far more than 4 million times the mass of the sun worth of just normal stars and gas. So it's by no means the dominant mass component of the galaxy. In fact, in general, the massive black holes at the center of galaxies are about 0.1% of their mass, 1 part in 1,000. So generally, they will not be dominating the behavior of stars further out, like the sun and the solar system.
The next question is specific, but I think it's an opportunity to talk about a more general question. So the 800 millimeter telescope project asks, do you have any updates on CAGRA, K-A-G-R-A, which is the cryogenic gravitational wave telescope, the large-scale cryogenic gravitational wave telescope? Can you talk a little bit about how it will contribute? And in general, what's the future for gravitational wave observatories or astronomy?
Well, the future is bright for gravitational wave astronomy, both on the ground and in space. The frontier, however, of course, of this type of research is in space, because we've never had a gravitational wave observatory in orbit in space. So I'll talk about that. That's a challenging thing to do. You need free-flying interferometers that can very precisely measure the distance between their elements to do what LIGO does on the ground with vacuum tubes and lasers and very, very accurate optics. It's the same principle. It's an interferometer. It's just operating as a free-flying system in space. And so we have CAGRA, we have LISA, we have the Europeans have their own upcoming mission, and so there's probably 4 or 5 concepts of gravitational wave observatories for space. A couple of them have had a proof of concept. NASA conducted a very important proof of concept about 2 years ago, and they have been green-lighted technically. They're feasible technically, but they're quite expensive projects, and currently, in terms of U.S. involvement in NASA, none of them has a big funding line, which is to say a wedge of money that's going to exceed $1 billion or more, which would be needed to develop one of these tools. So I would say this field is still 5 to 7 years away from coming to reality.
Excellent. The next question from one of, it's also related to gravitational waves. And the specific question, we'll do the same thing, is can we calculate the size of an object based on the frequency of gravitational waves? And what frequency should we look for to find the Big Bang mass of the early universe?
Yes, so it's a good question. Gravitational waves are very much diagnostic of the mass of the object that they emanate from and how that mass might be changing. So it's the gravitational wave signatures we've seen from merging black holes that give us the mass of both components of the merger. And so we do get a handle on the mass of objects that are releasing gravitational waves. When it comes to the universe as a whole in the early Big Bang, indeed it's possible and likely that there are gravitational wave signals from the early universe. Those are much harder to diagnose. First of all, their signatures are not as characteristic and don't involve such obvious periodicities and ringing effects as black hole mergers. It tends to be a more stochastic or noise-like signal. And the level of that signal is hard to predict from Big Bang theory. So at the moment, I don't think there are any mature calculations of what we expect the gravity waves from the Big Bang to be. But people are starting to use supercomputers to simulate this and trying to produce a plausible signal that we might be able to detect with the next generation of gravity detectors. The current generation is not capable of looking at gravitational radiation from the Big Bang. Matthew, you're muted.
I'm sorry about that. I was trying to talk and I did forget to unmute. And then more generally, can you talk about what kinds of things can we discover from gravitational waves? What are the possibilities? What kind of information can we glean from those at various wavelength regimes?
Well, they are, of course, very useful for detecting mergers of compact objects. So that's either black holes merging with each other, black holes merging with neutron stars, or neutron stars merging with each other. And we've now had signatures of all 3 of those type of events. They're also useful for detecting supernovae and understanding the nature of a supernova. If a supernova explosion was perfectly symmetric, gravitational waves from it would actually be quite subtle and hard to detect, but generally that's not expected to be the case. And some sort of asymmetric, slightly asymmetric supernova is a very strong signature, and that can be diagnosed with gravity waves. We also are anticipating, when we get these space-based systems, to be able to detect the merger of more massive black holes, and that's what we think happens in the center of galaxies as they merge and grow to the present day galaxies, and we've never seen this before, so that will be very exciting. And then the final frontier, as alluded to before, is the detection of gravitational waves or radiation from the Big Bang itself, and that's probably the hardest signal to detect.
Excellent. The next question is from David Gold, who's on with us live, who asks, since Uranus has an unusual axial tilt of a little over 90 degrees, could it be possible that Uranus's orbit around the sun is actually perpendicular to the plane of the solar system?
The orbital tilt is unusual, and that is imputed to be caused by an early collision or encounter, because that's not a natural thing to have a planet whose angular momentum vector, which is what the spin is telling you, is misaligned with the angular momentum vector of the entire solar system, which is dominated by the sun. So that's what we think about the orbital tilt. And I forgot what was the second part of the question.
Is it possible that its orbit is actually perpendicular
Right.
to the orbit of the solar system?
That would be possible, but it's not the case. We know that its orbit, it has an inclination, so it definitely shows an inclination, and that's because of the interaction of Uranus and Neptune. But it's not perpendicular. There is no planet in the solar system that orbits perpendicular to the ecliptic.
The next question is from Tina Weiss, who asks, what are your expectations of the James Webb telescope once it is calibrated? Will we get a completely new picture of the universe, and can you talk a little bit about what that it will look like?
It's going to take a while for James Webb to do its science. First images, science images coming in a couple of months. Probably take a couple of years for some of the big early projects to produce their results. One exciting project in the first year is a survey. With a new telescope and a new wavelength regime with a new sensitivity beyond anything previous, you're always smart to just do a survey as deep as you can over as large an area as you can. And so there's a survey, the biggest time allocation in the first round of observations is for a deep survey infrared in multi-wave bands. And that's probably going to find new things. That's going to find primordial galaxies, maybe primordial big black holes, and that'll happen in the first year. Also, the first exoplanet targets will be observed. There, the goal is to use the spectral method to sniff biomarkers or life-implied gases in the atmosphere of an exoplanet. Oxygen and ozone are the obvious ones. Methane's also possible, and you'd want to see water vapor too. So we'll see some of those observations in the first year.
All right, the next question is from an account called I Am Human Being 3, which makes me question if you're a human being since you have to state it so clearly. However, the question is, how does gravity affect a photon?
That's a good question. So photons are waves, electromagnetic waves, traveling at 300,000 kilometers per second, speed of light, regardless of their wavelength or frequency. But going back to Einstein 1905, we know that they have an equivalent mass. And so photons have momentum, clearly, and by E equals mc squared, they have an equivalent mass. And that means they are subject to gravity, as you would predict. Anything with mass should be affected by gravity. Now, the way they move in gravity is, of course, defined in general relativity by the curvature of space-time. And so the effect of gravity on photons is manifested as their paths in curved space-time, and they essentially follow geodesics is the technical term. They follow the paths of minimum energy, and so they follow curved trajectories, and that's mass-bending light. And that's a well-observed phenomena, and that's really how gravity affects light.
The next question is from Harry Bell, who asks, there are a number of interesting citizen science projects on Zooniverse, which is a website for those of you who don't know. Are there any projects that you feel are particularly worthwhile, or is it purely individual interest?
You know, they've grown so rapidly. Zooniverse is a very successful umbrella organization, if you like, for citizen science. And it goes far beyond astronomy. I'm on the mailing list of new projects, and they're sending an email more or less every week or so. And they're all over the place. I mean, they're well beyond astronomy. They're well beyond physical science. Some of them are archaeology, anthropology, zoology, botany. I mean, they're beyond life sciences, too. They're into very many different areas. So with that abundance of projects, which numbers well over 100 now, I think it is very much a matter of personal taste, which one you might prefer. But it's a well-run project organization. There are tools for measuring engagement and encouraging engagement with the people who use it, and rewarding them for the engagement are very sophisticated and well thought out, well evolved. So I recommend that project, and just find the thing that interests you the most.
And I will just add that they vet all of their projects. So anything that's up on the site is a good project, because they go through a very rigorous process of making sure that nothing goes up there that's not worthwhile. So the next question is from Wave, who's on live. And they ask, hello, could you speak a little about the structures at the edge of Saturn's rings, the mountain-like ridges?
Yeah, Saturn's rings has a lot of subtle structure, and I don't know that there's a very detailed explanation for these structures in the outer parts of Saturn's rings, but most of the structure in the rings, extending to the most dramatic structures, which is the Cassini division, the gap in the inner part of the ring system, are due to gravitational interactions or resonances. So basically, these particles are obviously in planar orbits around Saturn, but they interact. They obviously rub up against each other in their collisions. So there's evolution of the ring system in that way. But the most dramatic evolution is caused by the influence of the orbiting moons. Saturn has almost 100 moons, but it has at least a dozen pretty large moons. And the larger and closer in moons cause resonance effects which clear out some orbits completely, and in other cases induce more complex interactions that lead to the illusion of these mountains, or braiding, or notch marks azimuthally in the ring system. They're very striking patterns, and they're all caused by gravity.
Excellent. The next question is from Hernan Reyes, who asks, why isn't SETI called SET, S-E-T-T, instead, since what we're not looking for so much is intelligence, but extraterrestrial technology, since there could be hundreds of planets inhabited by dolphin equivalents, but we're searching for beings to communicate with. So why isn't that emphasized more in the field?
It's a good point, and the answer is simple. The answer is history and branding. SETI goes back to 1959 to 58, 59. That was Frank Drake's Project Ozma at the Green Bank Observatory, observing 2 stars, looking for radio artificial signals from 2 nearby stars to the sun. And all the way through the project, it's been recognized by the principals, people like Frank Drake and Jill Tarter, that indeed we don't know how to define intelligence fully on the Earth, let alone on some extraterrestrial situation. So what we're not actually searching for intelligence directly. We are indeed searching for technology. And we're only searching for certain types of technology. At the moment, we're primarily looking for civilizations that have powerful radio transmitters or powerful lasers. And the laser part was only been done in the last 20 years. So for the first 40 years, it was only looking for radio transmitters. So that's a pretty arbitrary pair of technologies to look for, when civilizations might have other more advanced technologies that maybe we don't have. So you only look for the things that you have yourself. So it's even more difficult than the fact that it's not looking for intelligence. It's only looking for very specific and anthropocentric, because it's to do with our civilization, our evolution as a technological species, examples elsewhere. And is that a limitation that makes it not worth doing? I don't think so. I mean, you do what you can, you do what you have the tools to do, and if you're doing it sensitively enough, then it's worthwhile. The projection of SETI's capability into the future is that within 10 years, SETI will have been able to see the equivalent of our Arecibo-type transmitters, our most powerful radio transmitters, on planets around the nearest 10 or 30 million stars. And at that point, if you haven't detected any of those stars having planets using radio transmitters, then I think you can probably safely assume they don't exist or they're not using that technology. It's a meaningful non-detection.
The next question is from one of our live participants, Jeff and Raja. So I don't know if you personally, if this participant can personally do it, but the question is, can I disprove the general theory of relativity? Is it possible? So I guess the general question is, is it possible to disprove the general theory of relativity?
Absolutely, it is. And in fact, it's a standard requirement of the scientific method. If you're following the method that leads to greater knowledge, you have to use theories that can be refuted, theories that are testable, and theories that can be, violated or invalidated by observation. And general relativity definitely falls in this category. So far, it turns out, as we do new experiments like detect gravitational waves, for example, as a brand new set of data, it passes all these tests very well, with flying colors, in fact, to the 4th or 5th decimal place in some cases. So GR is testable. It has been tested. It's passed all its tests, but people are continuing to push it. And so all the work we do in astrophysics and in situations of strong gravity in particularly, in compact objects and so on, is testing general relativity all the time. So it's continually being tested.
The next question is from Faisal, who would like to get to the bottom or understand a little bit more about redshift. So the light emitted by distant stars is shifted to red. Does this mean that it fades away if it goes further?
It does, in a sense, fading in a sense of being less energetic. So the redshift is caused by the expansion of space-time. So as photons from any source in the universe travel through space, that space is expanding, the space-time is expanding, and that means the waves themselves are being stretched by the expansion. Stretched means a longer wavelength means lower energy, and so the energy is being reduced. And in that sense, yes, they are fading away. In the far future of the universe, if the cosmic expansion continues, as we think it will because of dark energy, to accelerate, these redshift will become extreme. And things that we see now, like the microwave radiation from the Big Bang, those waves that are, millimeter wavelength now will stretch to be meters or kilometers or even much larger wavelengths, and their energy will become incredibly low. So in a sense, the microwave background radiation of the universe, its birth, the history of its birth, is destined to fade away as well as it's stretched by the increasing expansion.
Excellent, thank you very much. The next question is from one of our live participants. Keshav Kumar would like to know how many planets in our solar system have gravity?
Well, they all have masses that we can measure, and yes, they all have gravity. So gravity is an omnipresent feature of the solar system because any object with mass has gravity. And we can play the game, and there's sometimes you can see this at science museums around various places where they have, for kids especially, what would your weight be on Mars, or what would your weight be on Jupiter? You can't stand on Jupiter. It may not even have a firm surface. But that's a sort of way to convey the idea of gravity of the planets by imagining what your weight would be on the different planets.
The next question, I'm going to jump ahead because I think there's a really interesting one, and then we'll come back to the rest. Juan Carlos asks, hello, Professor. If you were chosen to dialogue with an intelligent civilization from outer space, what would be your first question?
Well, that's interesting, putting me on the spot. So you're dealing with an intelligent civilization. Somehow you've solved the problem of communication, which I think is actually a very profound problem. but let's assume that's been addressed, and you get to ask a question. I think I would probably ask them, I mean, I'm torn between two questions. I would obviously want to ask them how they had evolved their interactions with each other and with other species to live harmoniously on their planet. That's something that we haven't been able to do. That's the question I would ask them sociologically, and the scientific question I would ask them would just be, what are your fundamental laws of physics? Because we think we have some fundamental laws of physics, but we haven't reached a final limiting theory, and so it would be very interesting to know what they had come up with.
Good answer. So going back, Dion Mack, I think, is, I am 45 years old. In your opinion, is it too late to pursue a degree in astronomy? So the more generally, what would you consider too late? Or is there no expiration date?
I think for a degree, an undergraduate degree in astronomy, if you can afford to do that, to be a student at a later age, you have a revenue stream or income, or you're retired or working part-time or just can afford it, it's never too late. And there are examples, and I read about them all the time, of not just of students around the US who get their degrees at quite advanced ages, but even in science and even in astronomy it has happened. If, on the other hand, you want to get a second career going and do a career in astronomy, 45 is not necessarily too late for that, but it does make it challenging, because to get to the next stage, a graduate student is a longer job. I mean, the undergraduate degree is 4 years, essentially. A PhD would be another 6 or 7 on top of that. So at the point of trying to be a professional astronomer, which tends to need an advanced degree, you're looking at a decade, essentially, with a PhD. If you only had a master's, maybe that's 6 years. But that's quite a long time commitment for a pretty uncertain outcome in terms of whether there be a job available. So it sort of depends on what you're motivated by and what your career goal is. But as for studying astronomy as an undergrad, no, there's no age that's too high for that.
The next question is from Isha Dumail, who's on with us live. So you talked a little bit about the James Webb Space Telescope and what it's going to do, but can you maybe cover more specifically how it's different from Hubble and what it's going to do, how it's built maybe different than the Hubble Space Telescope?
Yeah, the comparison is important because Hubble is the premier space telescope for over 3 decades, and now James Webb is the new kid on the block. So why is it different? How is it better? It is different. I mean, it's better in the sense that it has more collecting area. It's a 6.5 meter mirror or set of mirrors. That's the equivalent aperture. And Hubble is 2.4, and that's a factor of 7 or 8 light gathering power. That's a big difference. So it's much more powerful in light gathering power. Its wavelengths are more longer wavelengths. Hubble had a very good instrument for most of its time called NICMOS that worked in the near infrared. But James Webb is primarily working in the near infrared, and it extends out to mid-infrared wavelengths. So the infrared capability of James Webb is unique and extraordinary, because the only previous infrared telescopes in space have been much smaller aperture telescopes. So this is taking space infrared astronomy to a completely new level, and that's something Hubble couldn't do. On the other hand, Hubble can work at optical and near ultraviolet wavelengths that James Webb can't. James Webb's optics are not good enough to make sharp images at short optical wavelengths, and it can't work in the infrared and the ultraviolet because it doesn't have instruments to detect that radiation. So there's things still that Hubble can do that James Webb can't. And the other difference, of course, is their environment in space. Hubble's in a low Earth orbit, and that occasionally has made problems. There's the South Atlantic anomaly, which is a geomagnetic situation which produces high backgrounds and increases the noise level in detectors. So there's a chunk of every 90-minute orbits where Hubble can't take useful data. And Hubble also has to deal with Earthshine, with the very small residual atmosphere that exists at that orbit. Whereas James Webb doesn't have to deal with any of those things. 1,000,000 miles from the Earth, Earthshine is negligible. It's a total vacuum out there. With the sun shield in place, you have a very dark, cold environment for doing observation, and that's very powerful.
The next question is from Omri Baron, who asks, can we say that we are not inside something like the Matrix? Is reality real? And what are some tests that we could do to figure that out, if possible?
I mean, I guess reality is as real as you think it is or want it to be. So there's obviously an argument, this goes back to philosophy of solipsism, where you could, as a coherent intellectual and philosophical position, you could question everything, including your own existence, including reality. So that idea has a long history going back hundreds of years. The modern incarnation of this idea, from the idea of the matrix and the simulation hypothesis of Nick Bostrom and others, is that an advanced civilization could create an almost difficult to determine from reality construct in a computer, and that we could be living in that construct. Can that idea be disproven? I think no. If the simulation is of suitable fidelity, then almost by definition you can't know that you're living in a simulation, because the simulation's perfect. And so everything you experience, down to the detail, will be simulated, and so you have no way to determine that that's the case. Some people think that's an implausible bar set too high on a simulation, and that reality would reveal itself, or unreality would reveal itself in some way. It's very argumentative, though. Scientists and philosophers simply do not agree on that aspect.
The next question is from Richard Kouzis. It is reported that some galaxies do not show the presence of dark matter. So how can that happen? And does it argue against the existence of dark matter?
It's true that some galaxies have negligible or almost absent of dark matter. And it's a very important set of observations. It's a very unusual and small set of galaxies, but they could be important. I don't think at this point those objects refute the idea of dark matter in general, because on the other side of the ledger we have hundreds or thousands of galaxies where we've got direct evidence for the dark matter, and hundreds where we've mapped it out. And so, dark matter is a ubiquitous feature of the universe, and we've seen it in many situations. And we believe it dominates galaxy mass. So those small number of galaxies that don't have dark matter, most of them are dwarf galaxies, it's attributed to interactions. So it is possible, especially if dark matter is not collisionless, which is a fundamental property of the particle that we don't yet know, whether dark matter particles suffer collisions with each other in addition to experiencing gravity, then it is possible you could have, through galaxy interactions and mergers, you could end up with stellar systems where the dark matter has been left behind or stripped off, or the stars have somehow escaped. So that's certainly conceivable. Either way, these are very interesting situations, even though there's a small number of them, because they are diagnostic of dark matter at some level, and so people give them a lot of attention.
The next question is from Ellensburg, Washington. Hello, can we expect to observe or detect dark matter in gravitational waves? Can they be somehow responsible for gravitational wave production?
Well, the relationship between gravitational waves and dark matter is interesting. It's tricky to define how we would see dark matter and gravitational waves. At the moment, the only systems where we get a strong enough signature to detect gravitational waves are compact objects. And a compact object like a black hole or a neutron star, it does have some dark matter. I mean, it's formed from a collapsed stellar corpse. But due to the nature of how it was formed, there's very little dark matter in a black hole. So they're not the best objects to look at for dark matter in gravitational waves. The place where we might see them is in gravitational waves from the universe, since the universe overall is dominated by dark matter. So looking at the early universe would be more a sign of an imprint from dark matter on gravitational waves, but we haven't detected those kind of waves yet, and they're very hard to detect.
The next question is from Energy Scientific. Did you see the Don't Look Up movie? And how scared should someone be about falling comets?
I did see the movie, and I appreciated it. I enjoyed it. It had a little wry social commentary and a good sense of irony. It was not a movie to be taken too literally. But the idea that it paints that there could be an impact on the Earth and of a catastrophic kind is indeed possible. it happens that the Earth gets an impact that's civilization destroying level of energy deposition every few tens of millions of years. It hasn't happened, we don't think, since the KT impactor that hit the Yucatan Peninsula off the coast of Mexico. So it has to be taken seriously. The scenario in the movie of the fear factor of it and the fright of it happening actually can be mitigated because we have enough early warning system that we're unlikely to be taken unaware or taken by surprise by it, as the tension of the movie involves, of course, the fact that we can't head off the collision, and so we're doomed by it. I think in real life we actually could head off a collision like that.
The next question is from one of our live participants, Ruchira Pal, who asks, what is your take on the Dragonfly mission to Titan? Yeah, we'll start with that. So the Dragonfly mission to Titan and what it entails.
So Dragonfly is a concept from NASA which is, keying off the very successful flying of a helicopter on Mars. And this is the idea of sending helicopters, or actually more like drone technology with rotors, to Titan to travel around within the atmosphere to settle on more than a handful of the bodies of liquid that exist there made of ethane, methane, and chemically sample them. And of course sample the atmosphere too as they do it. So a real wide-ranging reconnaissance mission. This technology is quite mature, and it's actually easier to do this experiment on Titan than Mars. Mars has 1% of Earth's gravitational atmospheric pressure. It's very difficult to fly rotor craft in that low density. Titan has an atmosphere density at the base that's even higher than density of the Earth's atmosphere. So we know how to fly in a thick atmosphere like that. So these are pretty reliable technologies. The only complication is, of course, operating them at a distance where they're so far from real-time command that they would have to be working on autonomously, essentially, and driven by a sort of AI software base to avoid them, making mistakes or doing the wrong thing.
The next question is related. Matthew Gutierrez asks, is it possible for Saturn's moon, Titan, to be reconsidered a planet, considering that it has the atmosphere and size of Mercury with these lakes of methane and ethane on the surface?
It's certainly true that by its size, its mass, its chemical complexity and properties, Titan is interesting enough that you'd want to think of it as a planet. But in astronomy, the definition of a planet has a different purpose, in fact. The definition of a planet is trying to capture that the object formed from the debris disk around a star and collapsed from material within that so that it orbited the star. And then a moon is defined as something that happens on that scale around a planet. So moons are just defined by how they formed. And since Titan orbits Saturn, we think it formed the way a moon forms, not the way a planet forms. And so it's always going to be thought of as a moon rather than a planet.
The next question is from one of our live participants. Taking into consideration the variety of biosignatures being researched to study exobiology, is the James Webb Space Telescope capable of detecting any of those biomarkers?
The James Webb is going to be able to detect some of them, but we should remember that the James Webb Space Telescope was planned over 30 years ago. It was planned before exoplanets were discovered. So its concept never included the idea of exoplanet study, and that means exoplanet research has had to be shoehorned into a telescope that was never built to do that, and that's a big limitation. And so some of the problems of those observations stem from that, and particularly what it means is the spectrographs were not built with the wavelength coverage that you would need for biomarkers. To detect biomarkers, you actually need more than one spectral line per element or molecule, and you need more than one molecule. So you really need some big spectral coverage and medium high resolution. And James Webb doesn't really have this. It's able to observe little bites of spectrum, and it's difficult. Each one takes a long time. So piecing together a biomarker searching spectrum is going to be very painful. It's going to take a long time. It's just not a very efficient science project for James Webb, but it will do it because it's an important science project. Also, James Webb is not operating at all the wavelengths where biomarkers will have their strongest spectral signatures, so that's another limitation.
The next question is from Hamza Ayaz, who asks, what are some of the most important questions in planet formation?
I think the most important questions are what is the range of initial configurations of planets in general? Because we know that planets can migrate, they can move around. So we're trying to separate out two things. We're trying to separate out what happens in a planetary system as it forms initially, so that's the initial conditions that lead to the way it looks right after formation, and then what subsequent processes lead planets to migrate or move around or reposition, as happened in our solar system, to give you the way a solar system looks after some billions of years later. So separating out those two things is pretty important. We also want to learn, probably, how the process of planet formation is affected when a star forms in a binary system or a multiple system, since most stars are not single stars. This is very important to know how binary or triple or more multiplicity of stars affects the nature of the planets around them, or in some cases, do no planets form? These are two big questions for planet formation.
The next question is from Harry Bell, who asks, are neutron star collisions a significant source of heavy elements?
Yes, it has been determined in the last few years, actually, that a significant fraction, possibly as much as a third or a little more than that, of the very heaviest elements, the rare earths and precious metals, as we would think of them, are formed in neutron star collisions. That means, of course, that the energy radiated from those collisions, which is gravitational energy fundamentally being turned into electromagnetic energy, heats to billions of Kelvin, sufficient for fusion to occur to increase the atomic number all the way up to the transuranic elements. So yes, neutron star collisions have been demonstrated by simulations and a few times by direct observation to be very important for heavy element creation.
The next question is from Krishna Buttada, who asks, is there any possibility of life on the Jovian moon Io?
There has been speculation about that early on. Someone, I think David Grinspoon, is a planetary scientist who's written in a mock serious fashion about life on Io. The reason it's even a conceivable thing is that life depends on free energy. Life has to have organic material, free energy, and we think liquid water. Io is a very energetic environment. There's a lot of free energy there. Also, it's not implausible that sulfur could play a role in biochemistry of an alternate type. Io, however, doesn't have liquid water that we know of. It may have some liquid water under the surface. So I would say it's a big stretch to talk about weird and bizarre forms of life on Io, but it's been done by professional astronomers, and so, you know, it's worth humoring them and taking it seriously. But I don't think we'll find life there.
All right, it is the end of our session. We have time for just one more question. So thank you all for joining us today. Aryan C asks, if we discover an intelligent alien civilization somewhere nearby, is it a sign of danger? Because they were talking about, they saw a video talking about the concepts like the Great Filter. And so how does that affect, us if there's another civilization nearby?
Well, yes, there's been a lot of debate about this, especially in the SETI community, because there also is a process called METI, which is messaging extraterrestrial intelligence, and this is the active form of communication rather than just a listening experiment. And there are some scientists, many astronomers, some famous people before he died, like Stephen Hawking, who just thought it was ill-advised to try and message civilizations, because if they were more advanced than us and malign in their intention, we might not survive the encounter. So I think there's, yes, a fair amount of concern or anxiety about the existence of an advanced extraterrestrial civilization, more advanced than us, say, would make us very vulnerable, clearly, to their intentions. Whether they're good or bad, we don't know. That's an interesting question to end with. We had a good range from comets to cosmology to aliens. I like the range and appreciate your questions, and thanks to you all and to Matthew for facilitating. I don't remember when our next session is, but I think we've got a couple more on the books.
Yes, that is correct. We have one more scheduled, and that is going to be in 2 weeks from now on Wednesday, April 6th. So hopefully we will see some or all of you there. That one's going to be on Twitch. And then we will send out announcements for the next few live sessions around that time. Thanks all for joining us today. We hope you have a great rest of your week, and keep looking up.